Hey everyone, welcome to the stream. So those of you who were hoping to catch me last Wednesday, unfortunately I wasn't feeling too well, so I decided to skip the stream. Last time I tried streaming when I wasn't feeling well, I didn't find that it turned out too great, so you know, best to take a rest when you need to. So, however, since last stream, I haven't been completely idle. Last time I streamed, we got to a point where we were trying to make, which game was it again? I think it was Mindstorm 3D. Yeah, 3D Mindstorm. We wanted to make 3D Mindstorm work. However, it wasn't, because it was just hanging on a black screen. And what we discovered was that, in effect, this game was waiting for a certain interrupt to occur, and for the CPU to basically run an interrupt service routine, an ISR. So I hadn't done any interrupt programming whatsoever for the emulator up until this point, and so I started looking into what that would entail, and started. Actually, I did a bunch of reading, and I'm trying to trying to find some of the stuff that I read. Here's one of the things that I read that was interesting, because we were looking at this schematic at some point, I think a couple streams ago, and I was trying to understand. So over here we have the VIA chip here, the 6522A, and I had remarked that here's the IRQ. There's an IRQ output, as it turns out, and this IRQ line here looks like it's connected to RAM. This is a RAM chip, which of course doesn't make much sense, right? And we had also noticed that there was an IRQ input here on the processor. This is the CPU. And this guy, well, we see that it's connected to one of the pins here. I think it's pin 36 on the cartridge. But there should be a connection between this, and it's not really showing up on the schematic. So I did some reading, trying to find information, and actually there's not much out there, but I did find this. This is on the Vid website, and Vid, by the way, is this excellent development, suite of development tools for making Vectrex games. It also includes an emulator, a C compiler, a disassembler, all kinds of really cool stuff, and lots of really useful docs. And this is a blog posting actually from not that long ago. And it's talking about this I think this card you can use, like somebody made a cartridge you can pop into the Vectrex. But in there he talks about this. He says the VIA can generate interrupts by timer, shifts, control lines, etc. And the schematics show the VIA IRQ pin connected to the RAM chips, which is nonsense, right? So that's pretty much what I was saying last time. This doesn't really make much sense. This right here, what is that, right? And he says what is nonsense is the fact that IRQ signals of VIA must reach the CPU, otherwise it would not be possible to generate interrupts at all by the VIA, right? So that makes sense. So that was one of the hints that it is, because for up until now, most of the ROMs that we run that work, they basically figure out which interrupts have been set by polling. They read the certain registers on the VIA through memory mapped registers, and they figure out, oh, this bit is set. That means this timer is finished. So that's one way to go about it. And I mean, polling is basically what's done when you're in a spin loop. And there's a lot of places where such a thing occurs. Like, let's say you emit. You set up the VIA to start rendering a line, and it starts drawing, and you basically enter the spin loop where you're waiting for the drawing to be finished, for when the shift register says that it's finished emptying or something like that. So there's or actually they usually use the timer for that, so they wait until the timer bit or the timer flag is set. However, all of these things can also generate interrupts, and some games use that. So 3D Mindstorm is one of those. So this is one of the things. And I also found on playvectrex.com there was this nice there's like this lecture from some university where they actually would program the 6809, which is the same CPU that is used in the Vectrex, and it has a whole bunch of information about interrupts in here. So I read these sections here, all of this stuff here, which is super interesting, and all that to say is that I started working on it. And let me go through some of the changes that I've made. I haven't actually committed these yet, but I made a few changes. So, okay, here in BitOps, I just had to remove some references because these, for read versions of the functions, I don't actually need to take the value by reference. This allows me to pass in, values that are temporaries, and it totally works. So that's not really that important. Okay, so yeah, this is part of it. Let me start actually at the via. So here, let's open a diff here. So yeah, here we see that the via, I added a function called IRQ enabled, which just returns true whether there's an IRQ enabled, and you'll see why I do this. Internally, I have a function called getInterruptFlagValue, and there's a reason for that as well that's related. The meat and potatoes is right here in the via, so let's go through that. So this is the CPP file. So we had this namespace for all the interrupt flags, and let me do this here. Okay, for the interrupt flag, and we previously only had timer 2 and timer 1 in there. So I went in and filled in the rest. Sorry, did I say timer? For the interrupt flag, exactly. And I also copied some comment here that I got from some other place that explains how each of these interrupt flag register bits are cleared, because I have to make sure that this happens. And in fact, I've pretty much taken care of most of this already previously, but anyways. So yeah, we have these bits here for the CA2 line, the CA1, CA2 and CA1. I think these are outputs. The shift output, the CB2, CB1, timer 2, timer 1 we already had, and then there's this magical bit 7 called IRQ enabled, which I will explain. This is kind of a special flag that gets set conditionally based on the other ones. Then afterwards, I added the one for the interrupt enable register. Now this is a register that we just had not implemented because nobody was actually using it to turn on or off interrupts. Like I said, most of the games we tested were just polling for bits in the interrupt flag, specifically just these 2 bits. And that's like, I think, the majority of games. But games actually can get interrupted for any time any one of these here gets set. These 6 bits? Yeah. 1, 2, 3, 4, 5, no, 7, of course. So any of these 7 get set, you can get an interrupt on the CPU, and you can handle it and figure out which one it is. But you also have to say which ones you want to enable. So it doesn't have to be any one of these. You can say which ones you're interested in, and you'll get an interrupt call for that, and that's what the interrupt enable register is for. What's special about it is also its bit 7 is kind of special. It's called the set clear control bit, and I'll show how that works as well. It's kind of interesting, really. So, okay, what do I have here? Oh yeah, I just kind of renamed the... Yeah, I worked a little bit on the shift register because the shift also has an IRQ line that may be pulled. Like it can also raise an interrupt when the shift is done. So that means that basically the shift register can shift 8 times. That actually should take 16 cycles, but due to a bug in the shift register, it takes 18 cycles. And so once those 18 cycles are complete, you can get an interrupt for that. It's supposed to, raise the shift bit here, bit 2. So I went ahead and implemented some of that, although I'm not even sure games are really using it, but it was very similar to how I did the timer stuff. So I renamed this to read value. So here in the case for interrupt flag, what I used to do was simply just set, like I would, build the interrupt flag locally here and set only the timer 1 and timer 2. I decided to wrap this up into a function because I need to use this elsewhere, so we can go over that afterwards. I had this fail message for whether interrupt enable was set or not. I'm probably going to just delete this line. But yeah, we are going to be correctly handling interrupt enable now. So yeah, I need to take a look again if there's anything special to do on read. I think it's just returning this flag's bit. This flag's value should be fine. And then, what did I do here? This is, okay, so this is for writing. And when we write to the interrupt flag, so here's a special handling I have to do. So right now I'm only actually doing this for shift timer 2 and timer 1. So yeah, right, basically if you write to the interrupt flags register, that clears interrupt flags for any bits that are enabled. Which I think is right. Is that right? Yes, I think that's true. If you just write any value whatsoever to interrupt flags, and I think most of the time 0 is written, but yes, it's really a special thing. So you write to the interrupt flag, any value, it'll basically clear them all. It'll reset them all to 0. When you read, that's a little bit different, and we're going to go over how the reading works. And if you write to interrupt enable, well, this one's different. This one is special as well. Bit 7 over here is used to know what to do. So bits 0 to 6 are like a mask. You say which bits you're interested in either setting or clearing, and then bit 7 says what is the operation you want to do. So let's say you set bit 7 to 0, then every one in bit positions 0 to 6. This is misspelled. So each one in a bit position is cleared, disabled, and then when bit 7 is 1, each one in a bit position enables that bit. Zeros in bit positions are left unchanged. So what that basically boils down to is I call my little helper set bits on interrupt enable. As a mask, I take all the bits except for bit 7, and I set those, so I create that mask out of the rest, and I say set that to whether or not bit 7 is enabled or not. So that basically handles exactly this interesting logic. So basically it's kind of cool, right? This interrupt enable has a special bit 7 that's used to say turn on these bits, like a command bit, and then the rest is basically the mask of which ones to affect. So I've got that for interrupt enable. Now at the bottom here, I'm just going to skip IRQ enable. So this is the get interrupt flag value. So this is when you read the interrupt flag. And the way that works is, again, bit 7 is special. So we go ahead and we start by building up the result. We initialize it to 0. Right now I'm only handling shift timer 2 and timer 1. So I go ahead and read what those values should be and set the bits based on those values. And then we set the IRQ enabled bit 7, if any of the bits are on in both result and interrupt enable, which I think is right. So the idea there is, like, if we have any bits enabled so far in our interrupt flag, and the interrupt enable has anything on, actually, from what I understand, then we go ahead and we set the IRQ bit to 1. And what that's supposed to mean is that once that's true, an interrupt can occur on the CPU. Now, whether the interrupt occurs on the CPU or not also has to do with the CPU, whether it has allowed interrupts to occur. So we're going to get to that. But the point is, it's like, you know, if some bit got set in interrupt flag and there is some bit set in the interrupt enable, that can cause an interrupt, which I find a little bit weird. Like, I would have thought it would only be caused if, you know, the bit that got set in the interrupt flag is also enabled in the interrupt enable. So it's yeah, it's a bit sure, but I read this somewhere, so I need to find out if that's true. I'm gonna put a little question here. Oops. So I'm gonna write here to do shouldn't we only enable IRQ if any of the bits in interrupt flags or in IFR is also enabled in the IER, the interrupt enable register. I don't know exactly what the right behavior here is. I'm gonna try and find it. I did find that doc somewhere, and I was actually sort of hunting for it, and I believe I found it from the vid toolchain where it has actually an excellent set of documentation, which I've actually copied here. So let me just see if I could find information on that. No, actually, I'll do that afterwards. I just want to finish up here. So basically, the get interrupt flag value, that's this helper function. And the reason why it's a helper is because this other function on my VIA called IRQ enabled, which returns true or false, will just go ahead and test and build this flag and see, is the IRQ enabled flag set? So basically the result of this here. I want to know if this bit got set or not. So that's the crux of the change. Now, if we just look at the rest is not much. There's just a couple of changes in the shift register. So yeah, I renamed value to read value. That kind of mimics more what I have for the timers. I added, like for my timers, set interrupt flag and interrupt flag to return it. And I have here, why did I make this mutable? Oh yes, because do I need this to be mutable? Let me see again. Read value. Yes, it's because of this read value. Yeah, as it turns out, when you read from the shift register, it actually resets it. So that's why I needed to make it mutable here. So when we do a read value, instead of just returning the value, we need to actually technically reset our shift cycles back to how many cycles we need to run. And I also reset the interrupt flag, which is mu. And in here, once we've done all our cycles, I set the interrupt flag to true. So this is how you're supposed to do the shift register logic for interrupts. So that's that. And then finally, this was sort of like starting to get it connected to the CPU in my debugger where we have our execute instruction. After we've, what is this here? After we, actually I don't know why I put it here. It's kind of a weird place to put it, but well, I guess I know why. So we're going to be doing a CPU instruction. We're going to update our VIA for that many, and then on the next iteration, we're going to see if VIA enabled the IRQ line. And if it did, we're going to want to pass that information into execute instruction. So we're going to add a parameter here that says, IRQ is, IRQ enabled or something. Like basically, do we need to raise IRQ? And then CPU will decide whether it needs to handle it or not. So yeah, and I just wanted to put a print here. So this actually does work. It's kind of interesting to see what happens here when we run certain games. So let's say I build over here. Let's give it a little run and we'll take a look. Okay, so if we run 3D Mindstorm, okay, so this is 3D Mindstorm here. We'll pay attention to the output here. Okay, so there's the game. Here, oh, there you go. So now we've got a whole bunch of IRQ enabled. Now this kind of spam is going to cause it to just not move forward because it's just happens too many times. But you can see basically on every single instruction that we execute, it's still on. And technically now our CPU should have handled this and jumped into an ISR and eventually cleared the flag. So we see though that for this game, as soon as it wants to start, the IRQ line is enabled. So that's kind of interesting, right? And I guess we could even technically check exactly which bits right now by reading. You see again, what is it again? I think it's D00, right? Yeah. So let's say D00, what would it be? Interrupt flag is D00D. So if we say print D00D, so we have C4, and I'm just also going to print the enable one, 7F. So that actually means all of the bits are enabled. So that's very interesting. So let's see here. C4. So I think Okay, so we've got here 0, 1, 2, bit 2, and bit 6. So that's the bit 2, so that's shift, and bit 6, which is timer 1. So those are two that are enabled right now, and that haven't been handled yet. So that's kind of neat, right? And actually, the fact that the enabled, I think really it boils down to the enable register. The very fact that it's at 7F, which means that basically all of them are on, is telling, right? We go back here to the interrupt enable, and of course, you know, bit 7 will be 0 because that's really only useful for when you actually need to write and set turn on or off. But when you read, it's always going to be false. Yeah, that bit will never be enabled and written into there, so it'll always be 0. So that totally makes sense. But yeah, so. So what this means is that at some point in this program, there would have been an instruction that wrote to D00E. Because if we reset, actually I can't, I'm gonna start all over here. So let's say we break, right? And for right now, if we were to print D00E, you see it's 0. We'll put a write watch, which is just a watch, on D00E to see when it gets written to, and we'll just run. So we should hit an instruction that tries to write. I assume it'll turn on all the bits. So maybe it'll write 7F to there, or maybe it'll write FF. Yeah, it'll probably write FF because it wants to turn them on all on. Okay, so here we've watched point hit. Write value is 82. So actually no, that's it. So 82. Interesting. So basically, we see what this wants to do is it says I want to turn on and know when bit 1 is going to be set. So that's interesting. So bit 1 was bit 1. CA1? Really? Fascinating. I don't really handle when CA1 gets set. Do I? Peripheral control. CA1 goes to SW7. 0 equals IRQ on low. 1 equals IRQ on high. Huh. So, okay, so that's actually interesting. So this game wants to know, it seems, when CA1's interrupt occurs, which actually I don't really know what that means. I have to kind of like look at this again. If we continue, that's it. So that's the one. That's the one it's interested in. One thing I don't quite understand though is it looked like, yeah, when I printed it later, it looked like it got 7F in there. So how come I don't see that? Or is there something wrong with the way I'm reading it? There might be a bug here. Let's see. Because we didn't get another another breakpoint for when that value gets written. So interrupt enable. Let's reset. Here we just return it. So actually, maybe the way I'm writing this is not correct. Let's take a look. We'll wanna start all over. Just make sure print D00E. Watch D00E. Okay, so we're in the process of trying to write this value. So interrupt enable is 0, and value got optimized away, unfortunately. So let's see if we can see what the value would be. Okay, so this basically became a single instruction. Move into CL. Moves the value in CL into, I guess, interrupt enable. And what is CL equal to right now? E4? E4. Why E4? That's not really the value we saw, is it? And if I hit F10... Okay, no, sorry, there's more code here. Alright, move AL to CL or CL with 7FH. So that's, okay, this is basically the mask. And it with 80F, which is bit 7. Move ECX into CL. ECX, 7F. So that's this here. Right. Branch, and then move. And then here we actually do the right back. And we end up with 7F. Is value 7F? Zero DEA. 0D 82. We're actually trying to write 82 to this value. Oh yeah, of course. Yeah, that's not actually what we want. What we want is we actually want to write to, we want to use 7F to mask in the values out of value that we want. So value is actually the mask. Value without bit 7. That's right. Okay, so that'll make more sense. If we run this again, we should see this work now. Okay, so watch D00E. And 82, and now if we do print D00E, there we go, it's got a 2. That's exactly what we expect. So this CA2 line so now actually given still gonna say IRQ enabled because why would it say that? Because that's it, right? Because we're saying if anything is enabled, if any other, again, I really wonder about this logic. I'm going to try and find the answer here. It seems a bit odd that we would cause IRQ to be enabled if there's no match between the interrupt enable line and the actual interrupt bit itself. Anyways, we can't really leave it like this because the game was waiting for CA1 and the CA1 bit will not be set, right? Because I'm not actually setting it. So I need to figure out what this means again. So peripheral control CA1 in the context of the Vectrex. Where can I find info about that? Okay, let's see here. See if we can find something about CA1. The polarity of output pins is controlled by an output register, and input data may be latched into an internal register under control of the CA1 line. This is about port A. Port A consists of 8 lines which can be individually programmed to act as inputs or outputs, true, under control of a data direction register A. The polarity of output pins is controlled by an output register, yes, and input data may be latched into an internal register under control of the CA1 line. So whether or not it latches onto that value is controlled by CA1. So this is more like of a general description. It's not related directly to the Vectrex, but let me just see what it says. The 2 port A control lines act as interrupt inputs or as handshake outputs. So this is CA1 and CA2. These are port A control lines. Port A0 to port A7, CA2. So port A consists of A line, okay, right. The two port A control lines act as interrupt inputs or as handshake outputs. Each line controls an internal interrupt flag with a corresponding interrupt enable bit. In addition, hold on a sec. Okay, so through peripheral control. So CA2, we know I am actually handling CA2. That's what drives the 0. But is this SW7? I gotta figure out. The two lines act as interrupt inputs or as handshake outputs. Each line controls an internal interrupt flag with a corresponding interrupt enable bit. In addition, CA1 controls the latching of data on port A input lines. CA1 is a high impedance input only, while CA2 represents one standard TTL load in the input mode. CA2 will drive one standard TTL load in the output mode. Alright, not getting as much information from that I was hoping. Let me see if I can find something. Let's look for CA1. Looks like I may have something about it in my notes. I'll take a look at that. I might have written it down at some point. Notes. Oh, okay, it's just a copy of this here. We may look for SW7 as well. Internal, maybe? Okay, let's see here. The 6522 PIA has a number of control lines that are sometimes used as handshake lines, as they can generate interrupts. But on the Vectrex, they are used to control the vector drawing hardware. CA1 IO7. This line is connected to the IO7 line of the AY3. This is the sound chip. My guess is that is used to generate an interrupt to the CPU. Huh. So it would wait. Maybe it's waiting for audio. Could that be it? That's possible. Huh. That's very possible. Okay, let's see what else we can find. Audio, right? And we saw also that it said SW7. We'll see if SW7 is related to audio as well. I do have an audio doc. I haven't really looked that much at audio yet. Here, let's see here. Okay, we just saw that. Oh, did it not keep the document open? That sucks. What was it again? Go to file. Okay, let's keep this file open. It said here IO7, and we can see here the IO7, probably this one here, IOA7. So it's saying it's connected to that. And what does it say about IOA7? Input output pins. This parallel input output port provides 8 bits of parallel data, 2 from the PSG CPU bus from 20 external devices. Okay, well, this is not giving me much information at this level. Okay, we could take a look actually at this hardware. Electro CPU via 6522. Okay, so this is what this is about. Okay, so this looks like mainly related to timers. Yeah, 2 timers. Timer B. Wow, this is like some very cycle accurate timings for when interrupts should be raised with relation to timers. I may have to revisit this at some point, but it's not really what I'm looking for right now, I think. 6522. think this is more high level stuff. It's a data sheet for the VIA. I really need, I think in the end it has something to do with audio, but I'm not quite sure. Maybe I'll go look here. This is just for that again. Vectrex, maybe here we'll figure it out. Wow, lots of information. You know what, let me take a look actually at this. So we're talking about the CA1 line, right? CA1 to SW7. So let's see what we see here. So this is the chip we're interested in. CB1. CA1, here we go. Yeah, okay, so we see it here. It is connected this way. It seems to be also connected to SW7. Maybe I should use a different color. Trying to get a bit confusing here, but CA1, SW7. So yes, it is connected to this port on the chip, but it seems to be also a connection down here, SW7, to one of the left controller's fourth input, which makes me wonder, is this something? That's interesting. Yeah, I don't think we're gonna find anything in here. The problem is these are all generic, and I need to understand how it's used specifically, how it's hooked up specifically here. I mean, my guess is something in the sound chip will cause this to raise the, to enable the CA1 line, or maybe it's the other way around, but it looks like that's what it would be. And another clue is this SW7, like the what we have here that says 0 equals IRQ on low, 1 equals, so like it sounds like if the SW7 is 0, then we set IRQ when SW7 is low. Or no, we're supposed to raise the IRQ for CA1 we're supposed to set the bit when SW7 is 0 or something like that. 0 IRQ on low. I don't know what we're talking about here. What would turn low? Basically, what it's okay. I think what it means is we set a value into CA1 here. If we set this bit to 0, it means that we expect an IRQ to be raised on low from the sound, from the audio chip. If we set it to 1, we expect the IRQ to be raised when it goes high. I don't know what goes low or what goes high, but that's what it means, at least at this level. Here we go. Port button. Yeah, so there is something about joystick devices here. CA1. Port 1 button 4 is wired to 6522 CA1 line. And port 0 button 4 is wired to the FIRQ line. So does this imply that the game would be expecting button 4 to be pressed on the second joystick? You know what? That's possible. I think 3D Mindstorm. Oh, that must be it. Yes. The light pen. This has to do with the light pen. Devices, except for paddles, on the joy ports usually only use the 4 buttons to communicate with Vectrex. Light pen, imager, link cables, VecSpeech. Actually, probably it's the imager for the 3D one, right? For 3D Mindstorm. Although in theory, all devices can be plugged into both ports, usually only port 1 is used for these devices, since the Vectrex user is used to having a joystick in port 0, and all programs making use of the devices have to adjust to the ports, and they usually don't do that. The only device known that actually is used in port 0 is the light pen. There is one program, Engine Analyzer, which expects the light pen in port 0. Okay. And let me just look this up. Maybe I should have looked this up before, but it didn't dawn on me that 3D Mindstorm. 3D Mindstorm. That is not useful at all. Can I not get a description here? Requires 3D imager. Okay, finally. This game sounds retarded than that. So yeah, okay, so this is what's going on here. This is a 3D imager game. I should probably identify those games because yeah. Do I not have it in my list? Oh, here it is. Oh, 3-D, that's why. Okay, so this is... Imager game. Looks for CA1. So, joy 2 button 4. Alright, well, we can still proceed with this. We'll just you know, I can enable I can map or connect the joy port 4 and enable CA1 when that occurs very easily. Actually, you can do that right now. And you know what? While I'm at it, I'm going to make this change that I think would be the right change. So instead of just testing if one or the other is set, we'll say set bits and the interrupt flag value. Okay, no, this is actually interrupt flag value. Yeah, set bits will enable bit 7. So interrupt IRQ enabled, and we'll do that if the result and interrupt enable so far 0x7f is non-zero. IRQ if any enabled bits are also enabled in IER. Let's try that, because this at least will mean that we won't get that output until the IRQ gets raised. So really, the idea here, I guess, is on a real Vectrex, is if you put in 3D Mindstorm and boot up and haven't connected your imager, then it will remain blank until you connect it. I suppose that's what it means. I don't really have an imager, so I can't test this theory, and I don't have any imager games, so I can't test it on my actual Vectrex. But it would seem that's the case. Okay, see, we're here and we're just in a wait loop. Print B00E. Yeah, so it's set to 2. And let's hook up that pressing button 4 will do the trick. So we can do that fairly easily. An update here. Joystick button state mask. So let's go like this. If input dot I don't have any query functions for that, do I? I should totally add that. Actually, you know what? I'm gonna first make a commit for what I have, and then we'll work on that. We have enough changes here to warrant just going ahead with committing this. Raised after all bits are shifted. What else? Yeah, that's good enough. Alright, so now let's do this next bit. Okay. So I was gonna go check out this input class and see if I should put in a, because we have here the ability to set buttons and set analog values, but I'd like to be able to query them back. So let's see here. Read by emulator. I'll say is button down or something. Or is button pressed? Maybe down is better. We'll give it the joystick index, the button index. Now what did I do here? Stick index, button index, oh sure, I can do that too. Got this mask that I build. And we'll just return read bits. Actually, we'll do test bit of that with the mask. Okay. So now we have a way to read back whether the button is down, and what we're interested in saying is if input dot if input dot is button down, joystick index 1, button index 3. So if that button is down, then we want to enable the CA1 line. I wonder if we should be, I guess it's always going to be updated. So it'll be something like set bits of, I don't actually have something for that, do I? So either I set a value, a bool or something, or maybe I should just set a bool. Say CA1 enabled. Keep it simple. We'll just say like this. This is not. Should make this const. All right, and then when we do our read for IRQ get interrupt flag value, we're going to want to set that one as well. So CA1 is, yeah, just above it. So we'll do this. Set bits result interrupt flag CA1 to whether it's enabled. Simple. I mean, I don't know if this is 100% accurate. We might have to do something again eventually with the audio chip as well. I don't know. But for now, we don't have audio, so set when joystick 2 button 4 is pressed, which is usually for 3D imager for peripherals. It's usually always on for peripherals like the 3D imager goggles. Now for this to work, I need to plug in my gamepad so that my keyboard becomes joystick 2. And then I can press the F key, which should be button 4. Okay, so let's see here. So 3D Mindstorm. Oh, that's interesting. Seeing as I did not press add input, did I write this wrong? Read. No, sorry, print D00E. And that's the. Now we need to print D00D, right? C6. It says on, yeah, so this looks like it got set to true. How did that happen? Let's see here. So that's false. Maybe it's this here. Oh, CA1 is true? Okay, that's interesting. Oh, right. I just remembered. Enabling actually is setting the value to 0, so it's the opposite of what we think. Enabled equals false. Okay, so the bit is set to 0 when it's enabled or 1 otherwise. So what we want to do here when we read is we want to test if this is false. Do the same thing. Okay. Because here what we do is we're storing the button state mask in the format that the VIA wants. So it's an 8-bit value where 0 means that the input is down and 1 means so like basically low is pressed and high is not pressed. So I need to use the same model for when I read. Okay. Now it should work the way we expect. Okay, so now we have a blank, nothing's happening, and then if I press F, there we go. And just to be sure, let's press other keys except for F. Make sure that it only gets set when we press that. Yeah, so I can press pretty much anything else, nothing happens, and if I press F, we get that bit set. Alright, great. And now if I print E6. Yeah, so that bit is raised. There's a couple of other interrupt bits that have been set. And the thing is that these will end up being cleared by the ISR most likely when we actually handle it. So, or at least the one of the bits will be cleared, I suppose. Although writing anywhere there would clear all the bits. So I don't know. We'll see. But I think it will clear them all because it's gonna say I've handled the one I care. I've handled the one I care about. I don't really care about the rest. So go ahead and clear it. Okay. Alright, so I'll say via enable CA1 interrupt when joystick 2 button 4 is pressed. Used by peripherals like the 3D Imager goggles. Alright, so now the next part is probably the most interesting part, is the CPU. Now for that I would really like to find that documentation that I had found. I had found this great doc, and it basically explains step by step what was expected to happen for when an interrupt gets generated. Probably not this. This looks like the data sheet. This is IRQ and NMI interrupt timing. Oh, by the way, I pretty much I read somewhere else also what the 3 bytes, you know, like basically on the Vectrex, in this specific case, like the 6809, so all 6809s expect the vector table to be mapped to these addresses. This is like hard-coded, you know, it's part of the way the 6809 is built. The Vectrex decides to map the top of memory, which includes this address space here, to the BIOS ROM. So that's ROM, and in the ROM, these vectors point to addresses in a section of RAM that can be written to by the cartridge. And what was confusing me was that actually each one of these points to 3 bytes in RAM. But I read somewhere, and it makes sense, is what actually happens is that, so ROM will, you know, say like here's the address to that location in RAM, and the program counter will be set to that. It'll literally just jump there, and then it'll start executing, and the 3 bytes are there so that you can basically write jump and then put some address. So 1 byte for the jump and the next 2 bytes for the address. So if a cartridge wants to have an IRQ, like write its own IRQ handler, it would do so by writing jump address of its handler that will be part of the cartridge ROM, and then it'll jump there and basically do what it needs to do. So yeah, that's basically explains why it's 3 bytes. So I'm reading here. A low-level input on this pin will initiate an interrupt request sequence, provided the mask bit in the CC is clear. Right, so there is a mask bit I, which is the interrupt mask bit. If it's not set, then we have to handle this. Now, since IRQ stacks the entire machine state, it provides a slower response to interrupts than FIRQ, which is up here. which we're not handling yet. And this we will need to eventually, if there's any games that use it. That's mapped to joystick 1 button 4, as opposed to joystick 2 button 4. Now, it says here IRQ also has a lower priority than FIRQ, right? So FIRQ would have to be handled first. Again, the interrupt service routine should clear the source of the interrupt before doing an RTI. So that's part of the ISR's responsibility. Wondering, where is this figure 9 that it was referring to? Figure 7, figure 8, table 1. Oh, here, figure 9, okay. Okay, well, I guess we can kind of see it here. Here it explains cycle by cycle what's supposed to happen. And I may actually, I think I do have a text file that shows this. So we can see here, let's see here, interrupt stacking and vector fetch sequence. IRQ or NMI happens here. There's M-2, M-1. Then it looks like it stores the 2 bytes of the PC. FFFF, I don't know why there's FFFF here. Then stack pointer -1, -2, -3. Okay, so this is where we're writing to the stack pointer, and then these are the values we push, I guess. So that's the PC low, PC high, user stack low, stack high. I wonder if this lines up with when we push the entire stack for, where do we do that again? Yeah, we have this here, the push operation. PC, then URS. Yeah, it looks like it would line up, and it would make sense because it would use the same hardware to do this. So PC, then the user stack, and after that should be YXDP. Yeah, YXDP A. Actually, it's B and A, and then the CCR. Okay. Okay, that's cool. Next bit, let's go see if we can find. I think I had it under CPU. Maybe here for cycles. Right here at the bottom. Hardware interrupts. Yeah, so here we can see each cycle what is supposed to happen. Okay, so that's what this refers to. We see here PC, PC, FFFF. I think this is like reading the program counter. That's what happens on the first 2. Then there's this third cycle that does nothing. And then we start writing to the stack pointer in this order. And then there's a couple more cycles at the end. So yeah, this should be pretty good. We can start implementing this, and we just need to make sure we calculate the right number of cycles. And yeah, we should be good. Then I think we might have to implement return from interrupt. I don't think I did that in my CPU. RTI, return from interrupt, which is 3B. Yeah, so we haven't implemented that one yet. So we'll have to do that as well, of course, because once it starts executing the interrupt, at one point it'll want to return, where we undo the pushing, undo all the stack, and bring back the state again. So, okay. I'm wondering if I should put a bool here or an enum to make it more clear when we call this what we're doing. Now I'll start with a bool. Okay, so I'll say bool IRQ enabled. Actually, like that. All right, let's see here. So I guess I would ideally want to reuse that logic, although maybe not, because that logic is all conditional. But let me just copy at least some of it. Push 8. So we're going to want to do push 16. We know it's going to be to S. Yeah. We need to do this. We need to push 16U. Push 16Y. X. TP. B. A. CC. And so how many cycles is this? 19? Is it always 19? I suppose so. And then here's the thing. I think we just want to return and not actually execute any more instructions than the actual IRQ handler. Yeah, we'll consider this one instruction, doing all of this. Yeah, I think that should be it. So let's see what happens. So what I'm expecting to happen is I'm expecting to see that we get, I'll press button 4, so I'll press the F key, and we should see a unhandled op fail message for the RTI, hopefully, if things go to plan. Oh yeah, I should return number of cycles. Have another return number of cycles? Yeah, I do. Okay. Okay, let's give this a shot. It's kind of exciting. Right, so here we will pass whether IRQ is enabled. We can get rid of this. So I'll press F. Okay. So I did not do exactly as I expected. That's interesting. So let's see if we can get some information. What if we print out the last 10,000? I don't know if that's not enough. Okay, actually, maybe let's go for 100,000 here. Okay, trace. So what we should be seeing, what should we be seeing? We should be seeing that actually, let me see if I can be a bit smarter about detecting what we're looking for. So we know that what do we know? We know that IRQ vector is CBF8. So let's see if we can find a CBF8 in there. No, CBF8. Does that make sense? Oh, actually, of course. I think I just realized I'm not fully implementing the logic for the IRQ here. I'm just saving the values in the stack, but we actually need to take we need to modify our PC, right? Exactly, we need to modify our PC to go to that vector, of course. And not this one here, but we need to jump. Is it a jump that I need to make? Let me see. Interrupt vector low, interrupt, that's it. On these two cycles, we're supposed to actually change our, we're supposed to read from these two vectors from memory at FFF8 and FFF9, and then put that in the PC. Yes, FFF8, FFF9. Okay. Yeah, pretty much like what we did here. So here we end up jumping to the ISR routine. Now when we read that, we don't actually jump. Here we're going to read this, and we're going to get back the address, which is what we just looked at, CBF8. So we should get CBF8. We'll put a breakpoint here and make sure that we get CBF8, because that's where we're going to be jumping to. Yeah, that makes more sense. Press the F key. 0E23, that is not what I expected. see something. CBF8. CBF8, right? Was CBF8 that we were expecting? Yeah. Why am I not getting that? Oh, could it be? No. FFF8. Maybe it's just optimizations here and we're not seeing it. Let me see if I can get a more clear picture here. CBFA, okay, so it's just the debugger is not showing me the right values. Man, it's really weird. I thought by now, even in release, I would not get values that are completely wrong. Okay, so this is still not quite what I expected. Let's print what's at CBF8. CBF8, CBF9, and then CBFA. So is 7E a jump? It is indeed a jump. So we should have executed a jump to location 0E5A, which is in the ROM. But we are actually at CBFA. What's going on here? Jump 05, yeah, 0. Interesting. Hey R3 Conic. Yes, indeed. My keyboard is broken. When you're frustrated reading too much assembly, at one point you just break your keyboard in half. I don't understand why. What am I reading here? I'm reading a jump to F35B, and for some reason it's saying write to unmapped range. Like, why am I doing a write to C459 and C458 here? Oh, because, oh, okay, I must have a messed up stack. What's going on here? Okay, let me try printing out my trace again. You know what we should do, really? Let's step this one thing at a time. As soon as we start our as soon as we hit our interrupt. So now if I go my debugger here, we'll just force it to stop. So CBF8, right? So part of the problem is that I'm handling IRQ enabled right away. There's something I'm not doing here. I think I need to, oh yes, I'm not respecting the I flag. Man, I'm really not handling this properly. Okay, let's see here. Yeah, so I need to be checking whether the mask bit is set first of all. Make sure that it's not set. And once we've pushed those registers, I suspect that we should be making sure that there's something that's not written here, I think, which is that that bit should be cleared or something, or we need to set the maskable interrupt flag. Okay, so it's not showing here, but there should be a place where we are playing around with our flags registers. So here's your interrupt mask, that's I. I read this somewhere about what happens when you do when you're implementing the interrupt. The CPU has to know that it's no longer. Actually, you know what? I think I know where that is. Oh yeah, there was something I wanted to say at the top of this stream. I totally wanted to address this and I totally forgot. So 8 Little Bits, who's one of my viewers, was kind enough to go ahead and I didn't really know about this, but there's this really cool list on GitHub, a list called Awesome Developer Streams, and 8 Little Bits went ahead and opened a pull request to add me to their list, and it just got merged actually. So I just wanted to say thank you to 8 Little Bits officially on stream. So what it means is if we go here on this Awesome Developer Stream, so that's on BNB, Awesome Developer Streams on GitHub. There's this really nice list of just a whole bunch of people who are doing developer streams. So if anyone's interested and you're looking for other developers, we've got this big list here. There's some people here that I know that I follow myself, like Suze Hinton. There's Ferris in here, over here, Ferris, Casey Muratori, of course, Hardly Difficult, a whole bunch of really great streamers. And now I'm on this list here at the bottom, right at the very bottom. So yeah, very cool. Thank you very much, 8 Little Bits. I appreciate it. I wanted to actually show this at the very beginning of the stream and I totally forgot, so sorry about that. Yeah, so where was I looking? I think it was this here. Yes. Yeah, this is the microprocessor lecture, is the one I was saying that's from some university where they were teaching the 6809, and I think it talks about everything we have to do in here. An order of priorities imposed. The interrupts at the top of the list, reset, NMI, set the flag bits of the other interrupts to stop them interrupting during the interrupt service routine. Okay. The former values of these bits are restored when the flags register is pulled off the stack. Okay, so that's for reset and NMI. That makes sense. Now further interrupts are then free to occur thereafter. The software interrupts allow interrupt facilities to be reached. Okay. Most of the interrupts cause all the registers to be stacked. An exception is the FIRQ. It is useful as it only stacks the flag register and of course the program counter. The user then has the responsibility for stacking the register that must be preserved. Okay, a record is kept in the entire flag in the flag register that only the flag register and the PC have been saved. So I need to set that for IRQ. So that when we do the return from interrupt, we know what to unstack. So for all other interrupts, E is set to 1. So that's something we have to do. To indicate that the entire register stack has been stacked, E is then referred to during RTI to determine how many registers are pulled off the stack at the end of the routine. As the flag register is always stacked, this is referred to after pulling to see whether only the PC is to be pulled or the complete set of registers and then the PC. Ah, okay. So the last thing that's stacked is the CC, the flags. So you always pop that, then you check whether E was set to 1. Okay, so then that means what we have right now isn't quite right. Let's see if we can fix this up. So first thing is we need to set entire to true. Oops. Before we push all of this, so that's going to be used there. But I am missing a bit more information. I'd like to know what happens for IRQ. Okay, the normal interrupt input is IRQ. The sequence of events when an IRQ signal is received. The process continues at the end of the current instruction, sure. If the interrupt mask is set, nothing happens, right. If the mask is not set, 0, then, so let's add that if in there as well. Complete processor status is stored on the system stack. The interrupt mask is set to prevent further interrupts. they mean set or unset? Yeah, sorry, that's it. So we want to know if this is equal to 0. So not masked. Then we mask it so that further that there we go. And then after that, this will be pushed as part of the CC here. And then when we restore it, it'll bring it back to what it was before. Does that make sense? Yeah, I don't know if this is supposed to be here or after we push. Because it says here, the complete processor status is stored. Then it says the interrupt mask is set. So this sounds more like it should be down here. What it's not saying though is about setting the entire flag. But surely this has to be set before we push because of what we read about for RTI. I should probably implement FIRQ at the same time since it's so similar. Okay, well, based on what we know, I think this is correct. So now at least we know we're not going to do... What was happening was we were chaining the interrupt multiple times. We were calling the interrupt service routine multiple times, which was wrong, obviously. So let's see how this goes now. This is not working, and this would be because the interrupt mask is 1. Why do I set these to true instead of 0 or 1? So apparently these are masked out when we start, but I would expect the program to then set this to 0 if it cared. Let's see here. What would be the flags? Trying to see if there's an instruction that would be used to set the flag's mask. This is the one, isn't it? Bit. No, this is not it. There was an operation that would set the control codes, the flags register. Wasn't there? .6809 set flags register. So the CCR. Clear carry, clear FRQ, clear RQ flags, clear overflow set. So these are what we're looking for. And CC. Set and clear instructions. Okay, because I guess it's because, right, here it is. Basically, if we do an and we pass in the CC value here, that's sort of what we're expecting. That, or probably in my case, it's an OR operation that we're expecting, like an OR CC 10 to set the RQ flag. This one here, 1A, or CC, inclusive or CC. So let's see if this is actually getting called, because it looks like it's not. Not getting called. I can't use the VS Code for this, it's so slow. I think this is the one that never finishes. So, I mean, maybe it would seem a bit odd that the program would not set that the IRQ flag to 0 itself. Is there any other way that we can set? Oh, there's always these set, oh, SEI, set IRQ flag. I know, but these are just, yeah, in the end it's still an OR CC, of course. Compound instructions, they're just helpers when you're writing assembly, but what they actually evaluate to is this. So yeah. Okay, why don't we try something? Why don't we try... I must have read somewhere that these get reset to 1 by default. I mean, I would assume so, and I would assume that a program would explicitly turn off the interrupt mask. That's what I would expect. Okay, so now if I press F, alright, so we hit it now because I initialized the interrupt mask to 0, which is probably wrong, but anyway, let's just see what happens. So let's go back to our debugger here, and turn on break into debugger. So we're now setting entire, okay, we're pushing the state, we turn off interrupt mask so that on the next hit, okay, we're in the debugger, we are at CBF8, we're going to do a jump now. IRQ is still enabled, but now the interrupt mask is there, so we no longer will run the interrupt. So that's good, right? So let's see here. We jump. So now this should be our interrupt service routine. We're going to 0E5A, which looks like that's where this ROM has its interrupt service routine. So let's just continue and let's see if we hit our missing op. And there we go. Actually, we have a CWAI, which is not RTI, but I think this is a, it is related to interrupts. I think it's a wait instruction, and we had looked at this before. CWAI and CCR wait for interrupt. Okay, that's interesting. So now, just to see, if we print D00E and D00D, so it still has that flag on. I'm just curious about this because if we are supposed to wait for interrupts, I would assume that the interrupt is disabled. Okay, so 0, 1, 2, so this bit is set. CWAI. Whoops. And CCR. So okay, there's a and CCR wait for interrupt. Okay, yeah, so this will be the next thing we have to implement. we have some kind of value in a register that we need to end our CCR with. That's probably to turn off some stuff and turn on, turn off bits we don't care about, I guess. Hey, thanks for the follow, Thiber18. Okay, so we need to implement this. And I just wanted to see, what does our trace look like? Yeah, because I really do expect that we should have seen some kind of, let's see here. Compare A09, D009. I'm just looking at anything that seems to be interfacing with the VIA chip. So this D009. Yeah, sorry, that is that. Timer too high. Timer too high. Okay, so it ran, and then at one point it was looking for, we can see that basically when it was comparing 1 against D009, which is the timer too high. Just waiting to see if the lowest bit has been cleared. Branch less to EA. Branch of less to 0040, which it would branch, and then at this point it's done. And then it says load B with 10, decrement B, so it's doing 10 decrements. So it's giving about a few cycles, and then load 0E75 into D, so 0E75, and then store that in CBF9. So this is a CBF9. Which interrupt is that for? CBF9. It's for IRQ again. So is this a new interrupt service routine, 0E75? I don't remember what the first one was. I'll have to mark that down. It looks like it's saying, let's store another interrupt service routine, and then let's wait for IRQ to be raised again so that we jump there. That's the thing though. I think from the looks of it, interrupt is still enabled right now. So if we step again, I think we'll be able to see this here. Oh no, IRQ is not enabled. Okay. Okay, that's good. Good and a little bit confusing. Because we printed D00E, which is the enable IER, and D00D, which is the actual interrupt register, and I thought we saw 012. Oh, okay, no, sorry, different bits. I got confused. Hex 2 is bit 1. So yeah, So it's not, okay, so it's not enabled. It did get cleared at some point. And so now it would wait until, I don't know what it's going to be waiting for. It depends on what the input is to CWAI. So basically we need to implement CWAI. That's the next step to this. All right, well, then I think I'm going to stop here because it is 11 and I kind of want to stop at 11. So I think we did some good work. We are really close. We need to implement CWAI and RTI, and we should have IRQ working, and then FIRQ should be trivial to implement after that. So, all right, so I'm gonna stop here, and if you guys want to see me continue on this, join me on Wednesday night around the same time. So yeah, thanks again for watching, and catch you soon.